Next, let's talk about waves and their properties. Richard Feynman once said, "If you've seen one wave, you've seen them all." So now let's talk about what waves are and what their properties are. So in chapter 2, I claimed that sound is a wave. So in science, claims have to be backed up by proof. In order for sound to be called a wave, we have to prove that it obeys all properties that other waves have. So in this chapter, we will talk about the properties of wave and how they apply to sound. Waves. How do you get something from one place to another? A simple answer it is, you take it there yourself. How do you transfer energy from one place to another? One way is to take it there physically yourself. For example, we want to transfer energy from one place to another. You can put that energy into a chunk of mass and you can send it to the other side. For example, if you want to break a piece of glass, you do not have to physically make contact with the glass yourself. You could throw a rock. By the action of throwing the rock, you will put some energy into the rock. This energy will travel with the rock until it gets to the glass, and that will shatter the glass. Similarly, a police officer, when he wants to subdue a criminal, he doesn't go up necessarily to go up and hit him. He can send an energy via a taser gun. So another way to transfer energy, which does not involve a transfer of matter, is by using waves. A wave is a transfer of energy without transfer of matter. So if you and your friend hold on to both ends of a rope, you can get energy to her by simply moving the rope up, back and forth. Although the rope has a back and forth motion, the rope itself will not move away or towards her. So only the information or the energy that you sent will get to her. So let's talk about some properties of wave. So most physicists only use some basic tools to describe the environment around us. One is called the particle model, and the other one is called the wave model. In particle model, we consider most objects to be point-like entities that have no internal structure. For example, Iman going down the street on her bike is a point particle. For the purposes of calculating her speed, acceleration, etc., we do not worry about whether she's drinking a soda can or if she's driving or talking with her brother who's sitting at the back of her. Wave model treats matter as waves. Waves are common and essential part of our surrounding and environment. Common examples of waves include water waves and sound waves. Waves are really important to human beings. 2 of our 5 basic senses are wave detectors. An ear is a sound wave detector, and our eyes are light wave detectors. A wave is characterized as a disturbance that travels away from the source. Particles in the medium that a wave moves through are disturbed from their equilibrium position as the wave passes through. Particles then return to their equilibrium position after the wave has passed. Now, some properties of the wave, as we have talked about them before, they can transport energy, they can transport information from one place to another, and they need a medium to do so. Note, the medium itself does not get transported. Just like here, if you were to look at the slide, what is happening here? The wave is moving through, but the particles in the medium are just going to and fro, back and forth, or in a circular motion as the wave passes through. A disturbance or change in some physical quantity is passed from point to point as the wave propagates. For light radio waves, a disturbance is a change in electric or magnetic field as shown in this picture, whereas for sound waves, a disturbance is pressure and density. In red, now note here, the medium reverts back to its undisturbed state after the wave has passed. So waves can transport energy and information from one place to another without any material particles moving from one place to another. It is almost like saying that we are transporting passengers from New York City to Selinsgrove without a bus. Basic kinds of waves. There are 2 basic kinds of wave, longitudinal and transverse. Longitudinal waves are those waves in which the medium moves back and forth in the same direction as the motion of the wave. Transverse waves are waves in which the motion of the medium is perpendicular to the motion of the wave. Now, in order to go further and define what longitudinal and transverse wave are, I need to define what density is. The density of a substance is its mass per unit volume. So basically, density is mass that an object has divided by its volume, where m is the mass of the substance and v is the volume of the substance. The SI unit of density are kilograms per meter cubed. In a solid, longitudinal waves travel at speeds e over rho, where rho is the density of the solid and e is the elastic, or also called the Young's modulus. Now, let's do a numerical problem. The question is, a particular alloy has Young's modulus of 1.1 times 10 to the 11 pascals and a density of 8920 kilograms per meter cubed. What is the speed of sound in the thin rod made of this alloy? So our question says that our particular alloy has a Young's modulus of 1.1 times 10 to the 11 pascal. So our Young's modulus is 1.1 times 10 to the 11 pascals. Our question also says is that it has a density, rho, of 8,920 kilograms per meter cubed. Now it's asking us, what is the speed of sound? So if this is a longitudinal wave, then the speed of the longitudinal wave will be equals to Young's modulus divided by its density, which is going to be 1.1 times 10 to the 11 pascals divided by 8920 kilogram per meter cubed. And I take a square root of that, and you can plug in your these numbers into your calculator. Once you plug in these numbers in your calculator, you will find that the speed that I calculated to be is 3,511 meters per second. Please make sure that I calculated this correctly. Next, for transverse waves, for example, light and electromagnetic waves, the speed is dependent on the dimension of the wave. For a wire or string, the transverse velocity is given by T over mu, where T is the tension and mu is the mass per unit length of the string. Now, what do sound waves actually look like? So this was the visible pattern of sound waves, a new technique of studying sound by focusing the acoustical lens on sound waves issuing from the horn on the extreme left. So basically, this is the horn that's producing the sound, and they have an acoustic lens, and you can see that these are waves that actually sound is traveling in.